During this last year, we've had the privilege of seeing SpaceX attempts to land the upper part of a Starship, doing the belly flop maneuver. But talking about it with some friends, I've realized that almost nobody has a good picture of the brutality of what they are trying to do. Mainly because it is very difficult to imagine how big a Starship really is. The upper part with which the landing tests were being performed is almost 50 meters high and 9 meters in diameter. That is, a 15-story building falling towards the Earth in a completely controlled manner.
Yes! No way! No way! Oh my God!
But have you ever stopped to think that from the incredible size of a rocket, only a tiny part is what we want to transport? The simplest example is in the Saturn V rocket that the Americans used to go to the moon. All this was launched from Earth, and only this tiny part is what returned. The reason for the enormous size of a rocket has its origin in all the fuel and oxidizer needed. That's the biggest difference with the airplanes. For example, an F-18 carries the fuel inside its wings. However, it uses the air of the atmosphere as oxidizer, since the air is formed, among others, with oxygen, and then the compressors of the engine are used to increase the density of the air. Then this compressed air joins with fuel and it all burns in the combustion chamber. However, space launchers go into space, so they cannot take advantage of the oxygen in the atmosphere for the combustion, and that is why they have to carry the oxidizer along with the fuel inside the vehicle. So yes, that's basically the reason why the rockets are so big, because they have to carry two tanks, one with the fuel and one with the oxidizer. But from now on this video, for making things simple, I will talk about fuel, but keep in mind that this is the sum of fuel and oxidizer. If you notice, in addition to that, space launchers have more than one stage. That is, they have an initial stage for launch, which makes them go up a certain distance, and later they detach and continue with the second stage. And that means that each stage must carry its own corresponding fuel. There are two main reasons why several stages are used. The first is because the thrust generated by a rocket is optimized for a particular altitude. This is determined by the exit area of its nozzle, but as the atmospheric pressure changes, the exit area of the nozzle should also change for the rocket to work in optimal conditions. As this could be very complex and expensive, what is done is that the second stage of the rocket that will be used at a higher altitude is optimized to give thrust in vacuum. The second reason why several stages are used is that when you use more than one stage and suddenly you get rid of one, the weight is drastically reduced, so for the same thrust force, the acceleration will be higher. Here we have the comparison in size between the Saturn V rocket used by the Americans to reach the moon and the Soviet competitor, the N-1. We will make an explicit video comparing these two amazing rockets, but for the moment, which one do you think was more powerful, taking into account that they are similar in size? Well, it really depends on the definition of powerful that we use. If we take into account the payload that they can put into orbit, for example, low orbit for reference, the Saturn could put up to 140 tons, while the N-1 only 95. If we compare, on the other hand, the thrust generated by each of these rockets at the moment of the launch, the N-1 generated a force of 45,000 kilonewtons, while the Saturn V 33,000. Since I know how complicated it is to understand the barbarity that this is, let me refresh you that the engine of the F-18 operated at maximum power generated about 80,000 kilonewtons, which implies that it would take 410 F-18 engines to match the Saturn V thrust and 560 to match the N-1. If you notice, the Saturn V can put more cargo into orbit, about 45 tons more than the N-1, while generated 12,000 kilonewtons less of thrust. How can this be? Well, that's due to the geographical situation of the Soviet Union. The Baikonur station, from where the USSR launched the rockets, could not take advantage of the rotation of the Earth as much as the Americans, who launched from Cape Canaveral, much farther south. For this reason, also the European Space Agency launches from French Guiana, almost at the equator. This is because all the points of the Earth go around in one day. However, the closer to the equator, the more distance you travel in the period of one day. And as speed is equal to space over time, the speed will be greater. But how much greater? This is something I've always wondered about. Just look at the differences in mass that can put the Saturn V into orbit with respect to the N1. At the equator, it is easy to calculate the speed on the surface of the Earth. Knowing the radius and that it rotates at 1 revolution per day, you get about 1,667 kilometers per hour. At Cape Canaveral, where the latitude of the Earth is 28 degrees, the rotational speed is 1,471 kilometers per hour. However, in Baikonur, where the latitude is 45 degrees, the rotational speed is 1,179 kilometers per hour. As you can see, it's a difference of about 20% with respect to Cape Canaveral, and in the aerospace sector, it implies a lot. It must be said though that apart from that, the Saturn V was more efficient in practically everything. It was much better at transforming the thrust force into movement, so therefore it didn't need so much thrust. It's also important to remark that the N1 didn't ever make a successful launch, but we will talk about this in a future video if we see that you support with the like button. With respect to the space launchers, mathematically what they do is to give a necessary increase in speed to a payload, usually a satellite, so that it is able to keep the orbit. Because as we explained a few weeks ago in the video about Earth orbits, to keep an object in orbit it is necessary to have a fairly high speed. That's what the rocket does. Give the increment in speed, which in the aerospace sector it is known as increment of v, or in a simple manner, delta v. And here is where the Tsiolkovsky equation comes to play. This part here is the ratio between the initial mass and the mass of the rocket without the fuel. We will do the logarithm of that, and then we multiply it by the gravity of the Earth at the surface. And watch out, because even if your rocket is on the moon or on Mars, the value of the gravity will be always 9.8, as if you were on the surface of the Earth. We will explain that in a few seconds. And then you multiply by the specific impulse, a very interesting magnitude always used in all orbital mechanics. In fact, if you look closely, the force never appears, and that is something I found difficult to understand. If you really like rocket stuff, it's fundamental to understand it. So let's go to it. The force is a momentary magnitude. For example, a rocket in a specific instance of a time will be generating a thrust force. However, if the rocket applies that force during a period of time, as it happens in reality, the impulse appears, which is force multiplied by time. But at the same time, it will be interesting to know how much fuel is spent to make that force during that period of time, and this is basically the specific impulse. But here's where the confusion comes. If you Google, you will realize that the specific impulse has units of seconds. How is this possible? Well, because at the end of the Second World War, which is when they began to study deeply rockets, the United States and the Soviet Union took the best German scientists, and in exchange for helping them to develop new projects, they could be forgiven for having been part of the Nazi side. But the Germans used the metric system, while the Americans used the imperial system. Just for those who doesn't understand the differences, in the metric system we use meters, while in the imperial system they use feet. So in order to avoid confusion, the agreement was reached to divide the specific impulse by the acceleration of gravity, using the units of the system that you are handling. In metric system, gravity is 9.81, while in imperial it is 32.2. In this way, regardless the system you use, the result of a specific impulse will be the same, since the seconds are the same in both systems. For this reason, even if we study a rocket that intends to go to deepest space, the value of gravity at the Earth's surface will be used, because it is just a convention to obtain seconds at the end. But another way of looking at the ESP is that for 1 kilogram of fuel, how many seconds is your rocket able to generate a thrust of 9.81 newtons? So as you can see, it really represents efficiency. The more seconds your rocket is able to generate that force, the more efficient it will be. This is the most intuitive explanation, but we wanted to explain the origin of this specific impulse, because I'm sure that, like me, many of you had the doubt of why the same value of gravity is always used no matter where you are. Well, having understood the ESP, we now understand perfectly the Tsiolkovsky equation, which tells us that the delta V depends on the logarithm of the masses multiplied by the ESP, and if you notice, also by gravity. This gravity is set to cancel the gravity that is dividing inside the ESP. I know, it's a mess, but now you can understand it. Well, with that, we can create a graph for a space launcher where the e-axis is the delta V obtained, at the x-axis the amount of fuel it carries. For example, the graph starts from the point 0, 0, because if you don't carry any fuel, you won't achieve any delta B, because your rocket is empty of fuel. But as we increase the fuel of the rocket, the delta B increases too, until if you look around this area, it seems to have a change in trend, and suddenly it stops growing. Which means that no matter how much extra fuel you add to the rocket, the delta B will not grow. And this is because there is a point at which if you put more fuel, you increase the total weight, and therefore you will need more fuel and you will increase the total weight, and so on and so forth. Something quite obvious but interesting to see it mathematically. The interesting part comes when we do the same thing but now for a two-stage rocket. To make sure you understand what we are doing, we put a rocket with an amount of fuel and calculate the delta B. We put a little more fuel and we calculate again the delta B, and so on with infinite points which allow us to draw a line. Well, by doing the same with the two stages, the rocket empty will weigh more, because the structure of the second stage with the fuel tanks, with another fuel pump, and so on. So this second stage adds weight, and therefore the delta B obtained for a single stage is higher at first. However, when we continue putting fuel and this exceeds a certain value, suddenly the graph of two stages is cut with the graph of a single stage, and the delta B obtained becomes higher. From this point, mathematically it is already more profitable to use two stages. However, in real life, where you have to spend money on design and manufacture, probably until the benefit of two stages isn't bigger enough, would be a better idea to just have one stage. The same analysis would have to be done to use 3 or 4 or even more stages. The Saturn V rocket was designed with 3 stages, or the Soviet N1 with 5 stages. However, the new Starship is designed to have only 2 stages, but here's a little bit of a trap, because for long-distance missions the rocket will remain at a low Earth orbit with a small amount of fuel remaining, not enough to reach a distant planet, but the rocket would stay orbiting a parking orbit and another Starship with fuel will be attached, and the fuel will be transferred to the initial Starship. At once full of fuel, it would leave to the Moon or even Mars. And obviously the Tsiolkovsky equation doesn't take that into account. In fact, in the same way, you can make an analysis to know what is the optimal distribution of the fuel in the space launcher. Imagine for a second that you want to carry 100 kilometers of fuel in your two-stage rocket. You could carry 70 in the first stage and 30 in the second, or 50-50, or 10 in the first one and 90 in the second one. Well, you name it. There are infinite combinations. Which of them do you think is the best one? Pause the video right now and put it in the comments, but do it. Don't cheat yourself saying that you already knew it. Solving the Tsiolkovsky equation for this infinite number of cases, an incredible graph can be obtained. The x-axis represents the percentage of the fuel that would go to the first stage. Therefore, fuel that would remain for the second stage will be the remaining fuel up to 100. That is, if we use the Falcon 9 data, this point will represent the case for which 20% of the fuel will go in the first stage and the remaining 80% will go to the second stage. And for this distribution, a delta B of 9.3 kilometers per second will be obtained. If we now represent all the cases, we can see the optimum speed increase. That is the fuel distribution that will give us the highest delta B. This distribution is approximately 87% fuel in the first stage and 30% in the second stage. This data is gathered after solving the Tsiolkovsky model ourselves, but if we now look at the real SpaceX value of the percentage that is carried in each stage, do you know where it is? Indeed, practically at the maximum. The reason why it does not match the maximum obtained in the graph is because the Tsiolkovsky equation is super simple. It doesn't take into account the drag generated by the rocket nor any other effect, but as you can see, it is an amazingly accurate model. If we want to find this optimal distribution for rockets with more stages, it would be the same process but a little more complex. But generally, all two-stage rockets will carry about 80% of the fuel in the first stage of the rocket and the rest in the second. This is because what costs more energy is to leave the Earth. Think that to put a satellite into orbit, you start from very low speed, and you have to fight vertically against gravity to give speed to the rocket. And taking into account that there is also resistance with the air in the form of drag, this part of the flight is where most fuel will be burned. This is because fighting against gravity in a direct battle is tremendously inefficient. Airplanes, for example, don't do that. they generate forward thrust, and the wings are the ones that generate the lift that is needed to fly. For example, an A380 generates a thrust of 350 kN with its 4 engines. However, it can transport a weight of 6,300 kN, so the lift is about 18 times greater than the thrust generated, and that is the key of aviation. Back to the rockets. Since SpaceX started broadcasting the launches live a few years ago, I've seen many times a generalized doubt: what is the max Q? As you can see in the little message display on the right, the max Q is the point where the dynamic pressure is the highest in the structure. Well, if we look at the definition of the dynamic pressure, we can see that it depends on the density and the velocity squared. And by the way, the dynamic pressure is always represented by the letter Q, so that is why we call it max Q. When the rocket is launched, the speed begins to increase, but as it ascends in altitude, the density goes down. So the max Q is the point where the combination of these two is maximum. Below this point, the density will be high, but the rocket will go at low speed, and above, the opposite. The vehicle goes very fast, but the density is very low. By the way, on the ground, before launching, as the speed is 0, the dynamic pressure will be 0. And the same when the vehicle is in space. There is no density, so the dynamic pressure is 0. Now, whenever you see space launches, you will understand much better the mathematics and physics behind them. Remember to subscribe if you are not, or take a look at previous videos, and always remember to think supersonic.